All right, so I guess I'm going to share my screen real quick, and I will show you guys kind of what's going to be on the test. All right, so can you guys see this, this Word document that I have up?
Yeah.
All right, so this is basically what's going to be covered on the test. So we're going to have the 6 derivative problems and 6 integral problems or antiderivatives. We're going to have a linear.
Is there any chance that you could email that to me?
Yes, I guess I could. I could probably email that out.
Okay.
So these are kind of like the things you're going to have to know to do these problems. And then we're going to cover a linearization problem, a tangent line problem, a definite integral problem, area between two curves, some related rates, an initial value.
How many related rates problems are there?
So all these are just going to be one.
Okay.
Yeah, and then there's going to be a two-part question at the end that's going to test your, I guess, conceptual understanding of some of the things that you've been working on in the past week.
Okay.
And so I guess this is where I feel like where you guys, I guess this is open to you. I guess what do you guys want to work on? Because I came up with example problems for all of these, and I should be able to walk through all of them with you guys. So I guess which one do we want to start with? Which one do you feel like you need the most help on?
If we have time to go over all of them, I think we could just start at the top.
Yeah, I was going to say that too. I just kind of want like a general overview.
So I guess we can start with our chain rule stuff. So I guess like this is just knowing the problem that's important, but I guess so some things. So I kind of like went through and said what's going to be tricky about this test. Can you guys see this whiteboard okay?
Yeah.
No, I can't, but let me try this. Okay, never mind. I'm good now.
All right. And so when I was looking at like chain rule problems, I think some of the trickier stuff is doing a chain within a chain. So
actually, David,
yeah?
Could you? Oh no, you're good. Just kidding.
Can you see that okay?
Yeah, I switched my view and now I can see better.
All right. Oh, am I still sharing my screen?
Yeah.
All right, that's probably why. Here, I'll stop sharing my screen so you can. So we have. All right, so like some of this stuff can get kind of tricky when we're doing like this. We have a square root within a square root. And so one thing I noticed is I was taking a test that's going to be really helpful is knowing what to do with these. So like being able to rewrite that. So I think that's like the first thing is we want to rewrite this as 7x plus 4 minus x to the 1/2 to the 1/3. And so I guess with the chain rules, I guess the concept behind a chain rule is we're just going to keep adding stuff on to the end of our problem. So as we go through and we solve this derivative, we're going to keep adding on to the end. And since we have a chain within a chain, we're going to end up adding 2 things onto the end of our problem. And so if we, real quick, we'll use the power rule, and we'll bring down this 1/3, and we'll write the inside of the equation. And we'll minus this by 1. So we're going to get this 2/3 power. And then we have to multiply it by the derivative of the inside. So on a chain rule, when we're doing this, so we're going to times this by 7 plus the derivative of this. But to do this, we have to do another chain rule. So we have to do a chain rule within a chain rule. And so once again, we have to do the power. So we'll drop the 1/2 in front. Am I writing off the screen yet, or can you still see it?
You're good.
We'll have 4 minus x to the negative 1/2. And then we have to do the chain rule again when we get to here, because this x is a negative. So when we take the derivative of this inside, we're going to end up with another -1 on the outside. And so
Sorry, can you say how you got that -1 again?
So if we look up here, and we're taking the derivative, so we have to take the derivative, we have to do the chain rule, so we have to take the derivative of the inside.
Yeah.
And while we're taking the derivative of the inside, we have to take the derivative of the inside again. So since it's 4 minus x, when we take the derivative of this, when we take a chain rule, the derivative of x is 1, but it's going to be negative, so the negative doesn't disappear. So this stuff is kind of tricky. Sometimes they'll sneak in these minus signs, and when you say, oh, the derivative of this is 1, well, that's close. It's a -1 because this is a -1x. And so when you take the derivative, we end up with a -1.
Oh.
So technically we have to chain it. So we took this chain rule, we rewrote the problem so it's a little bit easier to see what we're doing with the powers. And then we chain it, and then we chain it again. And in this particular problem, I don't know if there's like a whole lot of simplifying we can do because we have a whole lot of random powers in there, right? So I'd say we could probably just make this a negative and get rid of this -1 on the end, and it would also turn this one negative because it's this whole thing times the chain. Make sense? So I guess that's kind of what I wanted to cover with the chain rule. It's just like covering a chain within a chain, making sure you guys can understand that. So I guess, is there any other questions about doing a chain within a chain, or are we pretty good about that?
I think I'm good.
Yeah, I think I'm good.
All right, no problem. So I'll go ahead and erase this. So I guess the next rule that we have to cover would be the power rule, which are you guys feel comfortable about the power rule? I don't know if there's a whole lot there to cover other than as is probably one of the first you learned. I guess the only thing that like strikes me as important is knowing what to do with stuff like this, where a cube root or like a fifth root or like a fifth root squared, function squared, and like knowing how to read.
The fifth root function squared one?
This one? So it's just like this. So if we had something on the inside of this one, like an f of x, this is to the first power. So when we rewrite this one, it would just be to the 1/5 power. But if we took something like this, since it's to the second power, it would be to the 2/5 power. Yeah. So, yeah. And I guess just knowing that pretty much every time you see a square root, it's good to rewrite it when you're doing integrals and derivatives. So, and so we have a product rule. So let's look at this. So we have, let's say we have like 3x plus 4 times 7x plus 6. So this one's kind of simple. Oftentimes they'll throw in a chain rule by saying that this is to the third power, and then we have to chain it. But the product rule is simply the derivative of the first. So if we say that this is f of x and this is g of x, then it's just going to be f prime of x, g of x, plus g prime of x times f of x. And so if we're going to do this one's going to be pretty easy because the derivative of this is just going to be, because we have our first group and we have our second group, our f of x, g of x. So then we just end up with a 3 times 7x plus 6 plus 7 times 3x plus 4. And we could simplify that and make this a 21x plus 18 plus 21x plus 28. And so and we could say that this is our answer. I guess anything else you guys want to cover there, or you guys can see this?
Could you add like powers to both of them?
All right, yeah. So we could do it with
Work for
powers.
that? Like with the same things inside the parentheses?
Yep, we can do that. So let's say that this one's to the third power and this one's to the fourth power, right? So now it's essentially the same process where we have our two groups. We have our f of x and we have our g of x. So for now, we're going to have to chain it. So we're basically going to do the power rule. So we're going to have 3 times 3x plus 4 to the second power, and then we're going to have to chain it. So we're going to have to times this by an additional 3. And then we're going to times that by the 7x plus 6 to the fourth to finish off our first. So that's our f of prime of x plus, or g of x, right? And then we have to do it the other way. So g prime of x, f of x. So now we'll have this plus, and we'll do it here. So we have this 4 times 7x plus 6 to the third power. And then once again, we have to chain it. So we'll have to times that by a 7. And then we'll times that by our f of x function. So 3x plus 4 to the third power. So this is kind of complicated, right? So we can't really do much with the powers. So I would just multiply all our, to simplify this, I just multiply all our individual numbers. So we get 9 times 3x plus 4 squared times 7x plus 6 to the fourth plus 28 7x plus 6 to the third, 3x plus 4 to the third. And that should be our answer. That makes sense? Do you guys feel like...
Give me a second to write it down, sorry.
Is there anything else? Any other questions about this that either of you have?
I'm good.
All right. All right.
Sorry, 2 more seconds.
Oh, no, it's fine.
Okay, so I do have one question. So we are putting in that times 3 to the first one and the times 7 to the second one.
Right there? All right. One more time, question?
So I understand how to take like the derivative of 3x plus 4 to the third, like making it 3 times 3x plus 4 to the second makes sense to me, but why are we timesing that by 3?
So that's kind of the chain rule. So the chain rule, I guess if we like write it out, the chain rule, so we have a whole function that we're taking the derivative of. So when we do this, so if we had a function to a power, I guess we'll just write to the n. The power rule states that we'll have this n times this function to the n minus 1 times this all by the derivative of the inside function. So that's what the chain rule states. So when we get here, we have to chain this. So this is a function inside, so it's a function to a power. So when we drop the power down and we take n minus 1, then we have to times it by the derivative of the inside, which is 3.
Okay. That makes sense.
All right. So you guys both good with that one then? So
Yep.
Yeah.
all right. So I guess now we'll do the quotient rule. So we first have to have a quotient. So let's just take like 3x squared plus 4 over 4x plus 3. So the quotient rule states that we'll take the derivative. So this is one function. So this will be f of x. We'll call this one g of x. So we'll take the first function, So we'll take f prime x and times it by this g of x, and we'll minus from that a g prime of x, f of x. And we'll divide that all by the g of x squared. That's what the quotient rule is. So to do this one, we'll take the derivative of this top function. So that would be 6x. And then we'll times that by the 4x plus 3. And then we'll minus from that the derivative of the bottom times the top, which is 4 times 3x squared plus 4. We'll divide that all by the bottom squared, so 4x plus 3 squared. Then we could simplify this one by multiplying this 6x in and this 4 in. So then we have 24x squared plus 18x minus 12x squared plus, or that will be a negative minus 16 all over the same. So 4x plus 3 squared. So if we simplify that, we end up with 12x squared plus 18x minus 16 over 4x plus 3 squared. And if you really wanted to, you could factor out a 2 out of the top of this to make it look nicer, but I think this looks fine. So does that make sense for both of you?
Yes, it does.
And just like the product rule, we can make this more complicated by saying that this is squared or cubed or whatever, and then we end up with a chain rule in the end, right? So you can also have a chain within a quotient rule, and so let's make this to a high power. Say this is like to the 7th power, right? So now when we take the derivative of this first one, or instead of it just being the 6x squared, we're going to have this 7 times 3x squared plus 4, the 6th power, times the 6x. So we're just basically going to multiply everything by the 7. And then we'll multiply that by the 4x plus 3. Minus from that the 4 times 3x squared plus 4 to the 7th power. And that will all be over our 4x plus 3 squared. And then we could do some simplification on that with the same stuff. This will be a little bit more complicated since we have this multiplied here. We couldn't combine these two terms like we did on the last one. We probably have to leave them separate, but you guys get the concept, right?
Yeah.
All right.
Should I get up? Yep, sounds good.
All right. So now I guess we'll move on to integrals. So I guess things to remember about derivatives: rewrite roots into powers. Make sure you don't lose the negatives on chain rules, and watch out. Just always remember to add the chain on the end. So I guess for the integrals, the first thing we want to cover is the power rule, which is pretty simple. So it's basically an antiderivative. So the power rule, it's the exact opposite of the power rule of derivatives. So instead of multiplying and then minusing 1, we plus 1 and we divide. So it would be x to the 5th over 5. And then at the end of each integral, at the end of each indefinite integral, we always have to remember to add plus c, because there could always just be a constant at the end. So we always have to remember to add this plus c.
Have a cookie, please.
So any questions about the power rule?
Can I have 2?
No.
All right. So I guess, so like the first thing that I thought of when I was walking through the test is rewriting integrals algebraically before we actually take the integral. So let's say we have the integral of x squared plus 10x plus 21 over x plus 3. Now, this one looks kind of tricky, and you might think, well, we could do a u subs here, right? But like if we look at this, we can factor this problem, this top one, into this x plus 3 times x plus 7 over x plus 3. And then this becomes a really simple problem. Because we can just cancel out our x plus 3 in the top and the bottom, and then we're left with the integral of x plus 7. And then this becomes a much simpler problem than it was before. So up here, it's really complicated. Maybe if you did a u sub, it would be kind of hard. But then if we simplify it, we can get it to a much more manageable place. And then to finish this off, we just do the power rule. And that would be our answer. So I guess this is just one example. Other examples of like rewriting a problem algebraically could include something like where you have the integral of like, let's say like x to the 5th minus x to the 3rd all over x to the 3rd. Like, if we look at this, this seems kind of like a lot, but if we just rewrite this, so it's a fraction as x to the 5th over x to the 3rd minus x to the 3rd over x to the 3rd, then we can say that this is x squared minus 1. And then this also becomes a much simpler problem. So then that would be minus x plus c. And that would be our answer. Can you guys still see that stuff this far over on the board?
Yeah.
Yeah.
All right. So that kind of stuff makes sense?
Yes.
Yeah.
All right. So there's always like I guess a process that you can go through when you're doing an integral. So when you're first looking at integral, I think one of the first questions to ask is this a u sub? And if it's not, then you got to figure out some other way to do it. And a lot of times they will have it will just be written tricky. And if you simplify it, then it becomes a really easy problem. And just a word of advice, there's no problem that's undoable, because I know that the class may have covered integrals that you can't do. Some integrals that are really hard or impossible with what you know at the moment. They won't have any of that on the test. You'll be able to do every problem. So.
Okay, good to know.
Yeah. I guess the next one to cover would be u substitution on an integral. So if we just take this is a u substitution problem, and one pretty easy way to identify a u substitution is if we have some sort of function to a power. So this is 3x3 plus 4 to the 1/2 power, and that there's x's outside and inside. So you see how this is an x to the 3rd and this is an x squared. Every time we have that like difference of powers from the inside to the outside, that the inside's one higher than the outside, that usually means it's a u substitution problem. So if we take this, we can say that our u is equal to 3x cubed plus 4. And then we can say our du is equal to 9x squared dx. Now, we can kind of divide this 9x squared to the other side. And then sub this in, this for the dx. So now if we rewrite our integral, we have x squared times
Why do we
u.
want, because for some problems you don't divide the to get dx by itself. How do we know when to divide it?
Well, when to do this?
Yeah.
I guess so. When you're at this step, this du equals 9x squared dx. When we go from this step to this step, we want to solve for what this dx equals.
Always?
Yeah, so we want to replace this dx. You see how we have this dx in our equation? Well, if we're changing our u, if we're changing this to u, then we also need to change this dx to a du. And so by doing this step right here, then we get this dx is equal to du over 9x squared.
Okay.
And so that's kind of how we know we divide by this. Sometimes if we like take a derivative, like if this was a negative power, we have end up something on the bottom. And in that case, it would be multiplied. That makes sense?
Yeah.
So, all right. So now we have this, we can rewrite our problem to be du, and we can say this is over 9x squared. And so now we can see we have this x squared that we can get rid of. And now we're just left with u's and du's, which is what we want, right? So now in an integral, we can pull out constants. So to make this one even easier, we can pull this, essentially this 1/9 out of our integral. And then we're just left with this u to the 1/2 du. And then this becomes a simpler problem. So if we just take this up here.
And then we integrate it, right?
Yep. Yeah. So it'd be u to 3/2 over 3/2 plus c times 1/9. So that would be like 2 over 27, I think. And then we have to plug back in our u. So then we have our 3x cubed plus 4 to the 3/2 powers plus c. And that would be our answer, because I don't think you can simplify past that. That makes sense?
Yep.
So can you see this all the way over here?
Yep.
Yeah.
All right. So you guys have any questions about how to do this problem or anything else?
Nope.
All right. So I guess we'll move on to the next one.
Can you give me 1 second?
Oh,
I'm sorry,
yeah.
my roommate's just turned on a movie, but it's really loud, so I'm just gonna ask him to turn it down real quick.
All right, no problem.
Are we going to have any word problems like our last exam? Like,
Yes. So there are like 5, what I would consider word problems. There are 5 word problems on the test. So
I'm sorry, I didn't ask that question correctly. Are there going to, like, do we have to write the definitions of, like, what is the chain rule and write it out in words?
no, so you're going to have like one question at the very end of your test asking you to explain a couple concepts, but most of the test will be math. We'll be showing you work.
Okay.
So that was on the first test. All right, you guys both ready?
Yeah, sorry about that.
All right, so the next integral that we're going to do, it's called z sub. It's technically u sub. It's just kind of a special case of it. So you know how I said that if we have some function, if we have some inside function and the power is greater than the outside function by 1, then it's a u sub problem. Well, now we have this problem where if we treat this exactly like we did the last problem, then we're going to end up with this leftover x in our equation after we've written it to u's and du's, and that doesn't really work. So we have to approach this a little different. So like before, we're going to say that z is equal to x minus 7. But instead of finding dz right away, because dz is equal to dx. So when the time comes, we can just change this from dz to dx to dz. But before we do that, we want to rewrite this as x is equal to z plus 7. Now we can rewrite this function up here, this top one, as z plus 7 times z to the 1/2 power dz. And so beforehand, how it looks kind of like you can't really do that that integral, but if we rewrite it, then we can kind of get rid of this parentheses to the 1/2 power with this plus 7 inside, which is hard to deal with. So now we can multiply the z into our function. So we have the integral of z to the 3/2 plus 7z to the 1/2 dz. And now to integrate this, we can just use the power rule. So we can say that's z to the 5/2 over 5/2, or I could just write this as 2/5. And then we would have plus 7z to the 3/2 over like this. And then we have our plus c. So does that kind of make sense how we did that and how that differs a little bit from the u substitution problem we just did?
Yep.
All right. And then, like always, you have to make sure we plug in back since we started with x values, we want to end with x values. So we just want to plug back in our x values. So x minus 7 to the 5/2 over 5 plus 21 x minus 7 to 3/2 over 2 plus c. And that would be our answer. All right.
I'm sorry, so why do we times it by 3?
All right, so when we take the power rule up here, so we're going to go from z to the 1/2 to z to the 3/2 over 3/2. And so when you divide by a fraction, you just multiply by the reciprocal.
Oh, okay.
Oh, okay, that makes sense.
Okay.
Actually, I think you're right. I think it should be 2/3, because if we're dividing by 3/2, we need to multiply by 2/3. All right.
Yeah.
All right. This is a good thing to catch. So then this would be a 3 on the bottom, and this would be a 14. All right. So that would be our answer. Now we got it right.
Okay. Sounds good.
All right.
Could you possibly, are there going to be any equations where we'll have to find the derivative or the integral of an equation that has both a y and an x in the function?
Oh, implicit differentiation?
Yeah.
No. You won't have to cover that on the test.
Yay!
All right. So I guess if you have no other questions about z substitution and how we do that, I guess we can just move on.
So you do the same thing if it's like a 3x on the outside?
So if you had like a 3x on the outside, so if we had something like this.
Yeah.
Yeah, so it would look a little different, but I'm pretty sure. So if we say that z is equal to x minus 7, then x is equal to z plus 7. But then when we plug that back in, we're just going to have a 3 multiplied on the outside. And then we're going to have to multiply the z to the 1/2 in. So instead of just multiplying this in, we'll multiply them both in. Or if you really wanted to, you could just pull this out of the integral completely and leave it towards the end.
Okay.
So sometimes when I do this, I'll forget to write that down in the next step, and I'll lose points because I didn't carry my 3.
Yeah. So at the end, you would just multiply the whole thing by 3.
Yeah, you could do that, or you could multiply it in at this step when we combine these terms. You could multiply it in, so it's within the problem, or you could pull it out and then multiply at the end. But since it's a constant, it's not changing. So whatever we do with it, it's going to stay the same.
Okay.
All right. So I guess the next thing that we'll cover is a tangent line problem. So a tangent line problem, the information they'll give you some function, and they'll give you an initial x value. So it will be like find the tangent line of this equation at the point. That's a bad at sign. Sorry. At, let's say, x equals -2. So if we're going to find the tangent line, I think one of the first things to do is get your full point. So this is only half a point right now, and we're going to need a point to get a line later. So I think the first thing that I always do is I just plug this -2 back into the equation to get my y value at that point. So I get 4 minus 2 minus 3 equals -1. All right. So my point is going to be -2, -1. And I always usually organize it like something like this, where I'll put our point, and then we also are going to need a slope. And so I'll mark places on my paper where I'm going to put this to use later. And so now to find the slope, we're going to need the derivative of this. So that's pretty easy to find. Just use the power rule.
X plus 1.
Yep. And now to find the slope, we're just going to plug in this -2 again into this equation. So this would actually be dy dx, sorry. Or the rise over the run. And so that would be -3. So now we have our slope, and we have our point. So now we get to plug them into the point slope form, which is the y minus y1 equals the slope times x minus x1. So we'll have y minus 1, or since it's a -1, it's going to change to a positive, equals -3 because it's a slope, times x minus x1, which is -2, so it'll change to a +2. And that could be our answer. We could leave it as this form, or you could simplify it and make it so the y, so it's written like this, so you could just change it to be y equals -3x minus 7.
Which form does it want it in?
Either should be fine. This is technically a more simplified form. Sometimes you can just leave it as this, because this later on in upper level math class, it's really nice to have y's and x's on different sides. Like this, it tells it how it changes, but I think you'd be fine either way. I don't think you'd miss points if you just left it like this.
Will it specify that on the test, or you just kind of put it in whatever form you want?
Well, this is still an equation for a line. It just maybe not.
Yeah, no, but will it specify if it wants it in point slope or slope intercept?
No, we'll just say equation of a line.
Okay.
I think that's the wording on the test is it's find the equation of the tangent line to this curve. So I guess are there any other questions about this?
No.
All right. Yeah, this one isn't very hard. I like it when someone says find the tangent line. It's a simple thing. But so the next part, linearization problem, is very similar to a tangent line problem. Essentially, you're going to go through most of the same steps. There's just going to be a couple steps again at the end. All right, so let's say we have a line y equals the square root of x, right? And we want to use it to approximate the square root of 47.01. So let's say like 4 decimal places or something like that. So the way that we're going to start this, or let's change this to a 49. Sorry, 49. That makes it easier. So we already know that by looking at this, we should probably come out with something really close to 7, because the square root of 49 is 7. So the first thing to do on an approximation question or a linearization problem is we're going to find an x value that's really close to this, that's nice, that we know the square root of. So we'll just change 49. So let's say that x equals 49. And if x equals 49, y equals 7, right? So that's our point. So we have 49, 7 point. And once again, we're also going to need a slope to write a line. So we're going to take the derivative of this. So let's say y x to the 1/2. So we'll drop that. So y equals 1/2 x to negative 1/2. And now we're going to plug this like 49 back in to get our slope here. So if we take this, we can rewrite this as 1/2 times the square root of x. And we can plug 49. So if we plug 49 in there, we're going to get 1/14, right? And so now we have our slope, which is 1/14. So now we're going to use the same formula we used last time. We're just going to go y minus 7 is equal to 1/14 times x minus 49.
So just to make sure I understand, we don't actually want to put in the 49.01 in
No.
X.
So not quite yet. So what we're going to do is we're going to we're going to get this slope, this formula of a line. So essentially what we're doing is, so we have a curve that looks something like this, right? And we have this point. Let's say this is x equals 7, right? Or x equals 49. We're going to have this line that's tangent. So if we look at it really closely, when you look at it really closely, it's practically the same line for a long time. So this will be like x equals 49. Well, if we go to x equals 49.01, and we're using a line, it's not going to come out much different than if we were using it in the curve versus the line that we get. So it's called an approximation because it's not the exact answer, but it's going to be really close to our exact answer. So if we solve this one back out, we'll multiply this. So we have y equals 1/14x. And then we can simplify this by saying divisible by 7. So that'd be 7/2 minus 7/2 plus 7. And now what we basically do is we're going to take this 49.01 and plug it into this x equation to get our values of like what this is going to equal. So instead of doing it here, we're going to do it here, and we should come out with some answer that is really close to what this actually is. So so I think on the test, your numbers will be cleaner than this because I kind of just came up with this problem. So this isn't very clean. I think on the test, it should be a lot cleaner than this. So I'll use a calculator for this. But if when we plug that into our calculators, this word. So if we plug this one into our calculators, we get something like 7.000714. And if we use this, so if we just take the square root of 49.01, we pretty much come out. So, and then the square root of 49.01 comes out to be roughly exactly the same thing. So I guess it's just a different way of calculating square roots without actually doing a square root. It's kind of a weird one, but I don't know if it has much use anymore, but they want you to know how to do it. So
for our linearization problem on the exam, will it be a square root problem?
it will be very similar to this problem. Not this one, but very similar.
Okay.
Yeah. So, yeah, I think that there's other linearization stuff that you can do. Sometimes it's a different function, but it's kind of to approximate square roots. It's basically what linearization was for.
Okay.
So I guess things to remember is we don't use this number until the very end. So we want to pick the closest square root, natural square root that's easy to solve. So when we do that, we're going to be working with the actual number and not with its decimal in the end. So, all right. Are you guys good with this one?
Yeah.
Yes.
All right. All right. So we have like 10 or 15 minutes left. So I don't know if we'll be able to get through the rest of the stuff in 10 or 15 minutes because we still have to do like area between two curves, some related rates, initial values, min and max problems, and a definite integral. So what do you guys feel like you want to do first out of those?
Can we do related rates first?
All right. Yep, we can do a related rates problem. All right. I'll just grab my problem. So let's say we have a box or a cube. What? Let's say this cube has a square base of 5 centimeters by 5 centimeters. It's kind of a small cube. But let's say that we're pouring water. So we're pouring water into this cube to fill it up. And we're pouring at a rate of 6 centimeters cubed a second. And I guess, let's say, how fast is the height changing? When h is equal to, let's say, 4 centimeters. So I think one of the best things to do when you're doing a related rates problem is to keep track of all your information and write it down at the beginning. So we already have this h is equal to 4 centimeters. And then let's say
I was writing down the problem. What is h again?
it's our height. So it's how high the cube is. So let's say that this is h right here. So it's how tall a cube is.
Okay.
So we already have this little piece of information, right? And so what other information do we have? We know that our volume, our dV dt, so our rate is changing at 6 centimeters cubed a second. And we want to know how fast h is changing. So we want to know how fast our h is changing over time. So we don't know that. That's a question. And we also know that our base is 5 by 5 centimeters, right? So the first thing to do is to come up with a volume, an equation for a volume of a cube, which is pretty simple, right? Because it's just base times width times height. So volume, and since it's a square base, 5 by 5, we can say that it's x squared h, right? Our volume. That makes sense how we do that?
Yeah.
Or not x squared, or yeah, x squared. That's right.
Yeah.
And so now what we want is we want to know what our dH is. So, but we know what dV is, dt, because it tells us in the problem. So we're going to take the derivative of this function. So we're going to go the dV dt is equal to, and something that's right, this is easy to know, is in our cube, our square base is constant, right? So is x ever going to change? So x is just a constant, right? That no matter how high the cube is going up or down, that the x values are going to change. So it's like if we had like a cone, for instance, the higher up we go, the farther the radiance is going to get, right? And so if we were doing the same thing for a cone, we would have to treat x differently, or our radius differently than the side here. I don't know if that made a whole lot of sense. You guys catch that?
Yeah.
All right.
Basically, it's unchanging, right?
Yeah, it's unchanging. And because of that, we can treat this as a constant. And so if it's a constant, I just like plugging in constants in. So we can say that this is 25, or this up here is 25, right? 25h. And so now we have here, so when we're taking the derivative, the constant will stay the same, but h, our height, is dependent upon time. So just as our volume is dependent on time, so is our height. So when we take the derivative of h, instead of just it disappearing into a 1, we are going to have a dh dt out of it. And then we're just going to solve for a dh dt, right? So we'll plug in our numbers. So we have 6 equals 25 dh dt, and then dh dt is equal to 6 over 25. And that's how fast our height is changing at a given value. It's kind of interesting. Did our height matter at all? Do we have to use that number at all anywhere in our equation?
No.
Oh, why do you think that is?
I have no idea.
Well, if we look back at our cube, no matter how high we are, it's filling at the same rate. So if we like think of it as like a cone again for a second, when we first start filling it, it's gonna fill really fast, right? And as we keep filling it, it's gonna have more and more area to cover, right? Well, if we have a cube or something like a cylinder, as we fill it, the height isn't ever going to play a change in how fast it's filling. So if you have a cone, the height does change how fast it fills, or how fast the water's rising. As you get higher, the area gets bigger. But on like a cube or a sphere or cone, not cone, cylinder, as you go up, height doesn't really play any difference in it. So that's kind of an interesting thing that I saw as I was working through this, that sometimes your height plays an importance and sometimes it doesn't, and being able to recognize is kind of a cool thing, but I don't know if that's very useful. All right, are there any other questions about related rates? Or
Is the related rate question on the exam, is that dealing with cube, or?
No, it's not dealing with a cube. I don't want to give too much away, but it's not gonna be much harder than this one is.
Okay.
So this one's pretty simple. The one on the test is pretty simple. It's not something crazy.
Okay, because on the My Math Lab homework, there is this question about like an island in the middle of nowhere, and you had to use related rates to calculate exactly where you should swim and where you should walk.
Yeah, so it's not going to be like that. It's not going to be like that. I remember that problem. That problem was pretty hard. That took me a long time. All right. So I guess that's the related rates. I guess I had the. So you guys don't have any other questions about this?
No.
All right. So now I guess we have like the area between two curves, the min-max problem, and an initial value problem, and a definite integral. Which one do you think would be the next best one you guys want to cover before we run out of time?
You can pick, Kirsten. I picked last time.
All right.
Or whichever one you think was hardest. I don't know.
Yeah. Can we do the area under two curves?
All right. The area between two curves? Yes, we can do that. All right. I got to find where I wrote down the problem that I came up with the example. All right. So let's say we have the curve y equals x squared and y equals x plus 4, and the line at y equals x plus 4. So when you do an area between two curves, you're always going to want to draw a picture. So if we draw this picture real quick, then we have this like x squared function. All right, so there's our x squared function. And now, actually I wrote that down. I think this is something like this. Or no, sorry, that comes out wrong. All right, so we want a plus 2. So we're going to end up with something that looks like this. And we want to find the area in between these two curves, right? So essentially what we're going to do is we're going to find the area underneath this diagonal line. So like this. And then we're going to minus from it the area underneath this curve, or just this area right here. And so all we're going to be left with is this stuff in between. That makes sense how we do that? And so when we set this up, we're going to have the integral between of the top curve minus the bottom curve. So in this case, the top curve is a line. So x plus 2. And the top curve, bottom curve, is a minus x squared, or an x squared. So that's what our integral is going to be like. But this is going to be a definite integral since we have to evaluate it. So we got to find bounds. We got to find our a and our b for our integral. And a simple way that I like to set this up is where these points intersect, the x values of where they intersect. And an easy way of doing that is just setting the problems equal to each other. So we have x squared equals x plus 2. And we want to find where this statement is true. And sometimes you can just use some reasoning, or sometimes you can use a graph to figure it out. So it's really easy to look at the graph and say that this line intersects at x equals -1, and it intersects at x equals 2, right? And we can check it into our equation. And is this statement true for both these values? And it is. If we plug in a -1, we get 1 and 1, and if we plug in a 2, we get 4 and 4. That makes sense? And now we're going to use these for our values on our definite integral. So we always want to put the lower one on the bottom. So we're going to take the integral from -1 to 2 of x plus 2 minus x squared dx. And now we are going to want to take our integral. So we have x squared over 2 plus 2x minus x to the third over 3. We want to evaluate that at -1, and 2. So we'll plug in the 2 first to our equation. So we'll plug in the 2's.
Hold on. Wasn't the x squared negative to begin with?
The x squared, no, it's positive to begin with.
Well, when you put it into your integral problem,
Yeah, so
you're
we
minusing x squared.
yeah, because we do the top curve minus the bottom curve, and so it changes it to a negative, which is going to reflect up into our integral up here. That makes sense. How where the negative came from?
Yes, it does. Thank you.
All right. So then we'll continue to with this, and minus 2 cubed over 3. And we're going to minus that. So let's evaluate this real quick. So this would be 4 over 2. So that's 2 plus 4 minus 8/3. And then from that, we're going to keep evaluating this integral with, now we're going to do it the f of b minus f of a. So we're going to do this again with -1. So we're going to get 1/2 minus 2 plus 1/3. And it's a negative, so we got to remember to distribute the negative. So we have 2 plus 4 minus 8/3 minus 1/2 plus 2 minus 1/3. And then we probably want to change everything into sixths. But so we'll add all these together. So that would be 2, 4, 2. That would be 8. You can put those together, minus 9/3 minus 1/2. Well, this is 3. So that would be 5. 8 minus 3. 5 minus 1/2. And that would be 4.5 or 9/2. And that would be our answer. That makes sense how we got there?
Yeah.
All right. Any other questions on doing this? On the area between two curves? I think the important part is always remember to draw your curve, draw the picture, put the lower value on the bottom, and it's always top curve minus bottom curve. And sometimes this negative, like right here, can be, don't forget to distribute the negative. The negative right there can sometimes give you problems if you don't distribute it.
Okay. Is the there's only one of these on the exam? Is that correct?
Yep. There's only one problem like this on the exam.
Does it have on the My Math Lab? We had one where there was a quadratic and then there was an x to the 4th. Something like that, or something more simple with a quadratic?
It would be simpler, but yeah, sometimes you do end up having to do a quadratic formula to find where these points pass. So kind of how we set it up here, if we really wanted to, we could say that this is x squared minus x minus 2 equals 0. Or we could use the quadratic formula here to find our places, but it's kind of easy to see on this problem. But so the one on the test is it's more complicated than this one, but it's not like one that's sideways where you have to change it to x equals y kind of thing. Okay. So yeah, I guess any other questions about it?
Nope.
All right. I guess we have one time to do one more problem. So I'm thinking that probably we should do the, I guess, so we have initial value or the min-max problem. Which one would you rather do? Because they're both kind of difficult on the test. Both of them are kind of complex problems in the test. I'd say the min-max problem is probably a little bit harder. So let's do that one. So let's say we have a field.
Sorry, which one are we doing? Are we doing min-max?
Yeah, so we're doing a minimization problem. So we have, let's say we have a field. We want to build a field on the edge of a river to conserve fence space. So let's say we have a river, right? River. And we want to conserve fence space, so we're going to use the river as one side of our fence. So we're going to build a field. And we want the field to encompass 3,400 square feet. And so what is going to be the smallest amount of fence we can use? What are the dimensions on the fence going to be to keep this, but use the least amount of fence? To have the same area, but the least amount of fence is basically what our question is. Do I need to write that down, or you guys got it?
No, yeah, I'm good. At least.
All right. So the first thing that we're going to need to do on this kind of problem is, so we know that the area, so let's say that this is x and this is x and this is y, because these are going to be the same length. So we know that the area of the field is just going to be xy, right? But we also need to know, so what we really want is, we don't want area, we want perimeter, or because we want to know how much fence is actually going to take, what the dimensions are going to be. And so we know that the perimeter is going to be 2x plus y, right? And this is the we want to minimize the perimeter, but we can't really do that with two variables. Because if we try to take a derivative right now with this two variables, it's gonna, so you can't really do that at the moment. So we're gonna use this area that they give us, this area equation, to remove or substitute out one of our variables. So we're gonna have 3,400 equals x, y. So let's say that y is equal to x over, or 3,400 over x. So now we can plug this into that equation. So our perimeter, 2x plus 3,400 over x. Now we've solved our problem of having two different variables in our equation. So now we can take a derivative of this. So we're gonna just dp over dx, and that will be 2 plus, this is 3,400 to the negative, to x to the negative 1. So this is going to become a negative 3,400 over x squared. That makes sense how we did this step? It comes from here, so we drop down the negative 1, make it a negative 2, and then we put it back on the bottom, and it turns this negative. And since it's a minimization problem, we wanted to set this equal to 0. So we're going to say 0 equals 2 minus 3,400 over x squared. Now we simply want to solve this for x. So we'll say that 2x squared equals 3,400. We just rearrange the equation a little bit and multiply across. And we'll divide by 2. And x squared equals 3,400. So x is 1,700. So x is equal to the square root of 1,700. Let's see if we do that on our calculator real quick. That comes out to be about 41.23. So x equals 41.23 feet. So now we know the x, how far our x should be. But now we need to know how far our y is. So we're going to use this this area equation now to make it really simple. So we'll just say 3,400 equals 41.23 y, and solve it for y. So we'll just take that 3,400 and divide it by that 41.23, and you get y is equal to 82.46. So, and then this would be our answer about the dimensions, or how big our fence should be, to keep the same area but minimize the amount of fence we need to use. So, did that make sense? Yeah, could you guys follow along with that?
Yep.
Yeah.
All right. So, the one on the test, the problem like this on the test is probably a little more complicated than this, but it's the same process pretty much, just with a different problem. But
Is it a minimization problem or a maximization problem?
it's a minimization problem. But I don't think, if you guys can do this, I wouldn't be too hard. But once again, all story problems always start with a picture. Drawing a picture and being able to visualize it really helps on these problems. So on a story problem, draw a picture. Like, always do it. So like on the initial value problem, actually that one might be hard to draw a picture, but like the min-max problems and the related rates problems and like area between two curves, those are all picture problems.
Okay.
Yep. So I guess if either of you have any more questions before we end?
I think I'm okay. If you could email me that thing that you typed up, that would be awesome.
All right, I can do that. Is there anything you need, Kristen?
I think I'm good right now.
All right. Well, I think that's probably it for our review. Good luck on your test.